Hello everybody. Last section in chapter 3, related rates. It's tying together, of course, some 3, 4, 3, 5 a little bit, but it's also bringing in implicit differentiation. So we're looking to derive with respect to different variables, essentially. Related rates problems involve finding an unknown rate of change in terms of other rates of change that are known. So steps. As in most word problems, right, we want to start with a sketch. We want to organize our information, so we're listing our givens and our find. We are finding the equation that relates the variables. This is kind of background knowledge. This is a common equation that you've used in math or in real-world scenarios throughout. Then we're going to differentiate. There might be a hidden step, and I'll kind of go through a few of those examples. And then finally, we'll substitute all the information that we have back into the equation, and we'll solve for the missing. So our first example, pretty common, is a sliding ladder problem. Okay. So a 5-meter ladder leans against a wall. The bottom of the ladder is 1.5 meters from the wall at time t is equal to 0 and slides away from the wall at a rate of 0.8 meters per second. Find the velocity of the top of the ladder at time t is equal to 1. So with velocity, we've spoke about this, direction is important. Directions like up and right are both positive velocities, and directions like down and left are both negative velocities. So this ladder, starting against the wall like so, is moving away from the base at 0.8, and it's moving down the wall. Okay. So we want to label our triangle. That's up to you how you want to label it. You can give it meaning, or you can just be standard A, B, and C. Okay. What we know, what we want to find. Okay. Well, we know that the ladder is 5 meters. Very, very important. This is a constant, right? The ladder is not changing. There's going to be lots of variables in these problems that will change, so we always want to identify the ones that will not change. So anytime we come across a constant, we're going to put that value in immediately. All right, what else do we know? We know that the bottom of the ladder is 1.5 meters at time t is equal to 0. So b equals 1.5 at t equals 0. And we know that the rate that the ladder slides away from the wall is 0.8. So we label that dB, because that's what we labeled the base of the triangle, dt equals 0.8 meters per second. And finally, we're looking to find the rate that it's falling down the wall at time t equals 1. So we're looking for dA dt when t equals 1. That is our unknown. All right, so we got a couple of things to do. We've listed our knows and our find, or our givens and our find. We've drawn our picture. We've put in our constants. We need to come up with this equation that connects A, B, and C so that we can figure out what dA over dt is. Commonly, with a right triangle, when we have all three sides, we're going to be using the Pythagorean theorem. So a squared plus b squared is equal to c squared. Okay. So like what we had said before, anytime you have a constant, you want to insert that right away before you derive. Anything that changes does not get plugged in until after you have derived. So a squared plus b squared equals 5 squared. The reason that it's very important to plug this in is because as a constant, the rate goes to, or the term goes to 0 because the rate does not change. So then when we derive this with respect to time, right? So we're deriving dt, every single term. So every term is an implicit derivative, like in last section. So it would become 2a dA over dt plus 2b dB over dt equals 0. Okay. You can move things around. You can isolate dA over dt if you want to right now, but you don't have to. That's totally up to you. What we want to recognize is that we're going to input values with respect to time being 1. Okay, so think about how the triangle was formed in the beginning. When I placed that ladder against the wall, I started with the base being 1.5. That was at 0 seconds. We have to figure out, well, what's the base at 1 second? So if you think about the rate that the base is sliding away, right, this value right here, it's moving, the bottom of the ladder is moving to the right, and it's specifically moving 0.8 meters every single second. So therefore, at 1 second, the base is now 2.3, because I did 1.5 plus 0.8. And if I wanted to know at 2 seconds, then it would be 3.1. And then it would be 3.9, etc. So every second, we add 0.8 meters. So when we are ready to plug in, we don't have an A right now. We're looking for a dA over dt. We know our B right now, 2.3. We know our dB dt, 0.8, and that equals 0. So we currently have too many unknowns. We need to figure out what this A is so that we can actually solve for dA over dt. This is what would be considered a hidden step. Finding A. Now we can find A using the Pythagorean theorem. We now know that B is 2.3 squared and C was 5 squared. So we can solve for A, and we would end up getting 4.4. Okay. So a hidden step is sort of like you're ready to plug in, you're ready to find out what the final answer is, but you're just missing some piece, and you have to go back and figure out exactly how to find that piece. So if we now insert 4.4, and if we move things around, we would find that the rate that the ladder is sliding down the wall, specifically at 1 second, is equal to negative 0.42 meters per second. It makes sense that it's negative because the ladder is falling down the wall at this point. All right, example number 2. So we are now filling a rectangular tank. So water pours into a fish tank at a rate of 0.3 meters cubed per minute. How fast is the water level rising if the base of the tank is a rectangle of dimensions 2 by 3 meters? Okay, so let me draw my fish tank. Water's pouring in. I know that the base is 2 by 3. And I'm given this rate. I don't exactly know what the rate is standing for. So I have to use a little bit of clues to figure that out. So it says 0.3 meters cubed per minute. That unit is the giveaway. Because it's a unit to the third power, that means it has to be a volume rate. So this is equal to dV over dt. That's how the water is pouring in. Okay, so the volume of this fish tank is increasing at 0.3 meters per minute, And we want to figure out the water level rising. So we want to figure out H. We're looking for dH over dt. Okay. So if we know dV over dt and we want dH over dt, we have to think of a formula that connects volume and height. And we also already know the length and the width. So that's just volume of rectangular prism. Volume equals length times width times height. we have a constant here. The 2 and the 3 are not changing. So therefore, volume is equal to 6h. So now if we derive V equals 6h with respect to time, we have a dV dt equals a 6 dH dt. This is a linear relationship. So therefore, we can now plug in dV over dt is 0.3 equals 6 dH dt, and we can solve for dH dt by dividing by 6. And we have 0.05 meters per minute. Height is just a linear dimension, so it's just meters now. We've also essentially divided out the base, which is an area, which is a squared. So we divided out a meter squared in order to find this. Okay, so let's step it up. Let's do one that's a little bit more complicated. Same idea, but now our shape is harder, right? We're filling a conical tank. So water is pouring into a conical tank of height 10 meters and radius 4 meters at a rate of 6 meters cubed per minute. So there we go again. The unit's telling us that it's a dV dt, a volume rate. At what rate is the water level rising when the level is 5 meters high? So we want to find that dH dt again. Okay, so let's get our cone. So here's our cone. We know that the overall dimensions has a radius of 4 and a height of 10. And we have water pouring in again. And that is giving us a water level somewheres in here, right? With a height that changes and a radius that changes. What else do we know? We know that the dV dt is 6 meters cubed per minute. And we want to know dH dt when h equals 5. Okay, so again, it's a volume. I know if I'm given a volume rate, that means that I'm going to be deriving a volume formula. So the volume for this cone is 1/3 pi r squared h. Too many variables, right? We don't want to have a product rule here. We don't know anything about a dr dt, so therefore we don't want a radius in our equation. We only want a dV dt and a dH dt in our equation. We want to remove as many variables from the start that we can. So, using our drawing, we need to come up with a ratio. We have similar triangles essentially in here. So we can come up with a ratio in order to solve for r in terms of h. So we can say 10 is to 4 as h is to r, or whatever way you want to look at that. Okay, but ultimately, I need to isolate r. So now if I multiply by r, I have 10/4, or 0.4. I'm sorry, that's not 0.4. It will become 0.4 when I multiply. So right now I have r times 10/4 equals h. R equals, multiplied by reciprocal, 4/10 h, or 0.4 h. So that's the ratio that we need. That then will go into our volume formula. 0.4 h squared times another h. So our goal right now, we came up with our equation, but we're looking to simplify it as much as possible. Write it in as few variables as possible, and then even combine like terms here so that we're not dealing with a product rule. So volume equals 0.4 h squared is 0.16 h squared. So combining all of my coefficients here, I really have a 0.16 pi over 3, and I have an h cubed. Right, that's as easy as I can write this formula. Now I'm ready to derive it. So if I derive it with respect to time, I would have dv over dt equals, I have one variable, I have the power rule, and that's it. Right? Everything out in front is just a coefficient. So if I multiply by 3, the division of 3 goes away, so I have 0.16 pi h squared, attach my dh over dt for the implicit. All right, so it's fully derived. I just now have to insert all of the values that I know. So dv over dt is 6 equals 0.16 pi. We want to know when the height is 5 squared dh over dt. So now we solve for dh over dt, and we have 0.48 meters per minute equals dh over dt, specifically when h is 5. Two more examples. A spy uses a telescope to track a rocket launched vertically from a launching pad 6 kilometers away, as in figure 6, so I'm going to give it to you here. At a certain moment, the angle between the telescope and the ground is equal to pi over 3 and is changing at a rate of 0.9 radians per minute. What is the rocket's velocity at that moment? So again, the units typically are the giveaway for the rate that you are given. Okay, so I have my spy over here. They are looking at a rocket that's launching upward here. Excuse me. They are 6 kilometers away. That is a constant. That distance doesn't change, but the angle does change, and the height does change. Okay. I know, or I'm given, that the angle d theta over dt is changing at 0.9 radians per minute. I know that it's a d theta because of the unit radians per minute. We want to know the rate of the height. How fast is that rocket moving, specifically at the angle pi over 3? Okay. So what connects tangent with opposite and adjacent? Oh, sorry, I gave it away. What connects theta with opposite over adjacent? And that's going to be tangent. So tangent theta equals h over 6. I'm going to isolate h, makes it a little bit nicer looking. 6 tan theta equals h. Okay. Derive it with respect to time. 6 secant squared theta, attach a d theta dt, equals dh dt. All right, so I found my equation. I derived with respect to time. And now I'm going to plug in everything I know. So dh over dt, which is what I'm looking to find, equals 6 secant squared at pi over 3 times 0.9. Calculator's fine. I'm all right with that. So this is equal to 24 times 0.9, or 21.6 kilometers per minute. All right, last one. This one is definitely the hardest. The picture is a must here. Okay, so I gave it here exactly as it's drawn in the book. Farmer John's tractor, traveling 3 meters per second, pulls a rope attached to a bale of hay through a pulley with dimensions as indicated in figure 7. How fast is the bale of hay rising when the tractor is 5 meters from the bale? All right, so this picture, take a moment, try to understand as much as you can. Right, that X up top, that's the distance between the tractor and the bale of hay. The pulley system is 6 meters tall, and therefore the rope that drops down based on that h is 6 minus h. And we have a different triangle showing us that the distance between how the rope attaches to the tractor and the height of the overall pulley system is 4.5, okay, to make a right triangle. So the part that's not clear here that you really have to figure out is what the heck is the constant, right? There's so many pieces here that seem to be moving, and there's going to be too many variables if I think of it like that. But there is one length that doesn't change. Is overall length of the rope. That doesn't change. I'm going to call it L, which is the rope, which is a constant. Okay. Now, I have a couple of ways to come up with what L is equal to. Part of it is included in a right triangle, so Pythagorean theorem. So L is equal to the square root of 4.5 squared and x squared plus the 6 minus h. Right, there's two pieces of that rope. It's included in the right triangle, and it's included in the distance from the pulley down to the ground. So again, focusing on what we're actually looking for, we are given John's tractor, 3. Okay. We are looking for the dH dt. How fast is the bale rising? Okay. So we're technically given the dx dt, right? This distance that the tractor is moving is the 3 meters per second. So now with the equation that we have, we're okay because we have x's and we have h's. And therefore, if we derive it, we're going to come up with dx dt's and dH dt's, and that's what we need. So there's nothing I can do to clean up this equation. I just have to derive it as is. So knowing that L is a constant, I have no idea what the length is, but it doesn't matter. That's arbitrary. When I derive, L goes to 0. That's what's important. And now I have a chain rule, so I have a 1/2 inside to the negative 1/2 times inner prime. So 4.5 squared goes away, 2x dx dt, plus 6 minus h would go to plus 0 minus dH dt. Okay, so I'm just going to move dH dt over to the other side. It's pretty easy in this problem. And we're specifically looking when x is 5. So now I can plug everything in. The rest of the problem isn't so tough. It's really just acknowledging the fact that the rope is a constant, and that's the relationship that we really need. So everything else is pretty simple. Plug in, get your final answer of 2.23 meters per second is how fast the bale of hay is rising.